In the following, I will introduce the algorithms we have used. The first is the artificial immune system. It is a subfield of computational intelligence inspired by the principles and functions of the biological immune system. It has many properties that make it appealing to intrusion detection, and they are classified as negative selection, clonal selection, and danger theory. While the first two, negative selection and clonal selection, are more a traditional approach and discriminate between self and non-self to identify intrusions, danger theory is more recent and postulates that the biological immune system will respond to some forms of signals that are harming the host. The dendritic cell algorithm was derived from this danger theory. As a definition, DCA mimics the behavior of dendritic cells that respond to some forms of danger signals. And to do this, the algorithm combines some concepts. The first is the antigens, that are the items we need to classify, for instance, a process ID or a network connection. It combines them with signals that evaluate the context and return a mature context value between 0 and 1. In other words, the algorithm uses a population of DC cells that at first are immature, then start collecting antigens, and then become semi-mature or mature, meaning they can internally decide the local signals. The algorithm has three main stages, as it can be depicted in the image on the slide. The first is the pre-processing, in which we decide the antigen representation and the signal classification. For the signal classification, we can either use expert knowledge or automated processes such as information gain. Next, in the detection stage, cells start sampling antigens, and depending on the signals it will encounter, they might become semi-mature, meaning they've met more safe signals, or mature, meaning they've met more danger signals. Finally, in the analysis stage, the mature antigen context value is computed for each antigen type, and depending on the set threshold, we decide if it is an anomaly or not. For the central collector, as I previously said, we combine the swarm intelligence algorithm with support vector machines. Therefore, in the following, I will introduce the BAT algorithm, explaining our proposed improvement and how it can be adapted for our feature selection component. The BAT algorithm is a recently swarm intelligence algorithm that was proposed by Young, who was inspired by the echolocation of bats. Basically, the algorithm performs searches using identical individuals, each having an encoded location that defines the solution of the optimization problem, a velocity and a frequency, which are updated at each iteration. As it approaches the target, the individual will decrease its loudness and increase its pulse rate emission. And finally, to add exploration, the best solution is improved using random walks. The BAT algorithm is based on two components: exploration given by random walks, and exploitation by adjusting the loudness and pulse rate emission. Our proposed improvement addresses the exploration component because even though it has a the algorithm has a quick start, it quickly also loses exploration as the pulse rate emission increases exponentially, and therefore entering the exploration condition that is shown on the slide becomes less probable. Furthermore, the best solution is improved using small variation given by a decreasing loudness. And to enhance it, we introduce an additional term shown in red as a fraction of the Euclidean distance between its current position and a position attained by a neighbor, which has a better quality. To construct our feature selection component, we transform the BAT algorithm into its binary version by using the sigmoid function. Therefore, the solution becomes a string of 1 and 0s. We assume that the position of an individual is a d-dimensional variable, where each coordinate reflects the presence if 1, or the absence, if zero, of a feature in the subset. And to determine the quality of the solution or of the subset of features in our case, the machine learning classifier will compute the fitness function, which depends on the attack detection rate, false alarm rate, and number of features. Experimental results. To test our model, we use the NSL KDD dataset, which contains network connections labeled as an attack or normal. We randomly select a number of records from this dataset to test our local collector and central collector. We implemented our proposed version of the BAT algorithm, the original version, and the popular binary particle swarm optimization in order to compare them. We also implemented the dendritic cell algorithm, and for the classifier we use Beca, which is a library in Java. For the feature selection component of the central collector, our test results have shown that the attack detection rate is, the swarm intelligence algorithm managed to improve the attack detection rate by 10%, while the false alarm rate is reduced from 7% to 0.5%, while reducing the number of features in the best case scenario is almost 50%. Even though our proposed approach, shown in red, obtains similar performances when compared with the other swarm intelligence algorithm, it also requires fewer iterations, which is important because each iteration usually implies complex operations which are costly in terms of memory usage and execution times, and because it implies training and testing. For the second phase of our test case scenario, we use the local collector and obtain a good attack detection rate and false alarm rate. However, the suspicious data set was quite high, almost 8,000 records from 9,600. So further testing should be done in order to improve it. For the suspicious data set, our enhanced model obtains similar performances with the original algorithm, but with the mention that it has a lower complexity as it has fewer features. My main contribution in this paper is the anomaly intrusion detection model, which we constructed based on a local collector that performs a primary analysis and then sends the suspicious data set to the central collector. For the local collector, we use the recent artificial immune system, while for the central collector, we combine a personal improved swarm intelligence algorithm with the support vector machines. We improved the BAT algorithm, created a personal implementation, and tested our model on an established data set, which showed that our proposed approach can enhance intrusion detection. Future work will consider improving the dendritic cell algorithm with segmentation, hoping to obtain fewer suspicious data, and also adapting our proposed model to a more practical solution. We have thought about adapting it to an early-based warning system.